Free choice, yeah. So this is a talk that I did not write. Andrew Johnson wrote it, and he claims that it is the work of many people. And I will warn you that it's a little bit snide, and I think unfairly biased against state notation language. And I don't know why. I think, so anyway, let's just talk. The sequencer is the thing that actually runs a state notation language program at runtime. So at compile time, you write a state notation language program, and something that will remind you of C, but that has a specific syntax that I'll show you a little bit of later. That gets compiled into what is actual C code and then built into Epix, and that code will then be run by the sequencer, which is which comes from the seq module. So I think effectively what happens is that the sequencer gets embedded into your code and it will run. But I don't know the details of it because I haven't really looked at the source of this. And it's intended for state machines where you can identify that you're in some state and where you can identify a transition, some event or action that takes you from state A to state B. But that's not the only kind of problem for which state notation language is used. It's also just handy because it's a nice way to write C code in the IOC and to write a channel access client in an IOC and not have to worry about all the channel access stuff. I mean, you're going to have to identify the PVs that you're talking to, but you don't have to go through all putting monitors on and having callbacks. The sequencer does all that stuff for you. So here's an example. You're in the low vacuum state. If the pressure goes below 5 microtorr and that's continuously monitored, you want this thing to put itself into the high vacuum state. And then if the pressure goes above 5 microtorr, we're going to go back into the low. And that's the kind of thing that's easy to do in state notation language. So here's the syntax of all the states. This is embedded in a state set, which I'm not showing you. This is just an individual state pulled out of a state set. And this state is low vacuum. Someone's going to send us here. So when we get here, we know that somebody intended for us to be in this state. And then all we have to do is, when the pressure is less than this, we execute these, we set these PVs, and now rough pump is going to end up being associated with an Epix PV. That we don't see that association here. That happened upstairs a little bit. But then we can write 0 to the roughing pump because we don't need that. We don't need that guy anymore. And then we can turn on the cryo pump and write that PV. And then we can, I guess, open the valve or whatever. I don't know exactly what these things do. And then once we've done all that stuff, we can go into a different state, high vacuum, and then our behavior in response to pressure or something might be something completely different. So that's generally how that works. Nope, that's not how it works. Here's how it works. So here's the state set that I told you about. And up top, you have the syntax that you have to have is defining values that are going to be used here and assigning those values to Epix PV names, and then deciding whether or not you want to monitor those values. And there's other possibilities as well. You can also have events associated with those values.
And when you say monitor certain PV, how do you know with which frequency you do it? Oh, it's already set for this one.
In this case, monitor means put a channel access monitor on that, so we're going to get an event whenever that thing changes value.
Okay.
Outside of its MDEL, its
Okay.
monitor delta field.
Okay.
So somebody else is in charge of sending us those events. So that's a complete state notation language program, and a reasonable example. That gets translated into C code that you are intentionally not able to see. The point here is that it's not that much. And there's the object code, in case any of you guys prefer machine language. So one advantage is that it's compiled code, which is fast. It's going to be faster than like a calc record or a database that has to make states from one to another. It can call any C++ code. You can have code that's not really involved in any of the states, that's defined outside of any state, that's just a function call. You can define that stuff in there too. It has easy connections to channel access, as I said. And it's a good way of implementing state machines. So I think a problem has to reach a certain level of complexity before I'm willing to do this. Simple stuff I'm just going to do in a database, but I'm not the only person in the world, and there are guys who jump straight to state notation language programs for all kinds of problems. And I mean, you can use whatever tool you feel confident using, I think. The disadvantage is that the runtime debugging is not all that great. And the disadvantage, being able to call C++ code is also a disadvantage because you can get into trouble, and it might be hard to see that trouble.
Do you have an example of how C++ is called in the sequences? There's like a double % sign.
I don't remember. Yeah, I think it's
not something obvious.
It's either a double % for a single line that you don't want the state notation language compiler to look at, but to just translate directly. And if you have a whole section of code that you want, then you can %ampersand. And I think that it might even show that. So the risks of writing, I don't really know what this is for. The risk of writing SNL code is that it starts out easy and evolves, and it can end up as a convoluted mess, which I've done. So I think that's right. But you can also just start over and do it right, now that you know how you want that problem to be structured. So it's like any other code. And here's the snide part, I think. Good reasons, if you have a statesy problem, if you need to do fault recovery, that's hard to do in a database. And startup and shutdown are also sometimes hard to do in a database. And if you can't do this if you don't know how to do this with a database, then that's a good reason to use the sequencer. And I don't want to deal with records. I'm more comfortable with C code. It's said to be a bad reason for using the sequencer. But actually, I'm okay with that. I think people should use tools that they feel competent using. And it might be a good idea to develop expertise in other things that are more appropriate to problems, but I like people operating at what they think of as their best and most secure. So if you really want to use SNL, I mean, really, I don't understand this tone. I don't have anything, I mean, I've written a lot of SNL code, and maybe I'm the target of this stuff. Who knows? But I think it's really good. There is a good manual, and I think it's always good to implement in small steps. And I'll say one other thing. I never start an SNL program from scratch. I don't think I have started anything from scratch since about 1996. I always go grab somebody else's example of what they did and then look at it and then throw away most of the code and then substitute in my code. I don't know. And I think that's a pretty good way to work, especially if you take a model from somebody who's a better programmer than you are, which in my case is not a hard problem. So the structure is you can have some name, you can put comments in here. In C, there are options and variables and state sets. Option R, I agree that this should be the default. That allows you to have 2 copies of this state notation language program running simultaneously. I think if it's something is worth writing in SNL, you're probably going to have several copies of it. It's not always true. You can, if you want, start right away and not wait for channel access connections. And I never do this because what I want is for this program to tell me that no, this PV doesn't exist, or you typed something wrong, or there's something else, somebody didn't load that database.
Maybe fitting what re-entrant needs.
I'm sorry?
What re-entrant means, can you please say it again?
Yeah, reentrant means that in the middle of, because there's only one copy of the program, right, in the Epic's IOC, but there are two instances of it running, the thing has to be able to keep track of where it is, and that means it can't store anything in a local variable or in a global variable. Everything has to be local so that we can task switch and two different applications can use the same code. So in order to do that, the code has to be written in what the software developers call a reentrant style. And this just tells the SNL compiler to write reentrant code, which for our purposes mostly means don't use any global variables.
So if I don't do this and I run 2 copies of this, I may get into trouble.
Yes, you will certainly get into trouble because you're going to have variables no matter what. And when one program runs, it's going to be writing to the values of those variables. And when the other program runs, it's also going to be writing to the values of those very same variables.
But how I can have 2 different copies of IOCs? Actually, I can. Okay. But if I have only one copy, I may not even care about it.
Right.
Okay.
If you have only one copy, then you don't care whether those variables are stored in global or local space. But it's never a problem. I think it should be. The difficulty with this is that it complicates the business of calling external C code. Because now your code is not going to be run through the stuff that's external C code is not going to be run through the SNL compiler. Maybe I can get an example of that. Right, escaped C code. If you're in here and you write something that uses variables that are in the state notation language program file, the state notation language compiler is not going to touch those things and is not going to turn them into local references into references that are specific to the instance of the program. So you have to do that yourself, and you do it like this. Actually, maybe it's even worse than that. No, I think it actually is worse than that. Oh, I don't have an example of that actually happening, but you just need to know that when you select reentrant and call external C code that references variables, you're going to have to pay attention because you need to also include the identifier the way the state notation language compiler would have included it. There's plenty of examples of that actually. In the SNL code for the monochromator in the optics module, for example, has callouts like that. So the variables have to have type, and that's pretty similar. You assign a variable to a PV name like this, and then you say to monitor or not. You can have shorts and strings. You can use macros, and these macros are specified by the user in the invocation of the program. After IOC init, you'll see a line in which the program is invoked, and that's where those macros come from. You can have array variables, and you can have event flags, which I'm not going to get into. Right, I don't see any event flags here. I guess I should get into it. An event flag is basically a local variable that you attach to the change of state of some some PV.
And you define it in the very beginning of the code.
Yes, and I think I don't see that being done
It's
here.
okay. Okay.
Yeah, it's declared like this, event flag, and then you can sync that a variable name with that event flag.
And this event flag, this variable name has to be 0 or 1, or it can be anything. So event will be sent anytime it changes.
It can be anything.
So if it's an analog input, anytime that it changes, even a tiny bit, I will have an event flag.
Okay, I think I misled you earlier. The event flag is associated with a local variable.
Okay.
The variable, in turn, can be associated with the PV, but the
Okay.
event flag is not directly associated with the PV.
Okay.
So it's associated with the change in value of that variable. And we don't, and that variable should be monitored, otherwise it's not going to make any sense to have an event flag attached to something that can't change of itself. So here's an example of somebody setting an event flag. And testing an event flag, and you can test and clear an event flag.
Can you
We've
go
already-
back one?
Yes.
second? So when we clear the event flag and then we test it. And what does it do?
It tests whether or not the event flag has been set, presumably by somebody else.
Okay.
So, in some state, you can set an event flag, and then somebody else can come around and test it and
But
find out
there's
whether.
no actions associated with the test.
No, there isn't any action. It's just the is this variable set or not.
So in this code, when this some flag is tested, what do we do? What this line does? When you have test some event flag, what this line does? Just test it and no actions?
Yeah, this is pulled out of something larger, so it's hard
Oh,
to see
okay.
the context.
Okay.
So
Okay.
I think all by itself doesn't really do
Okay.
anything. I think it's intended to be an example of the syntax of that. So this is what you do if you want to use escaped C code. The state notation language code will add pvar to all the state machine variables that it recognizes. But if you're using escaped C code, you have to do that yourself. So I don't think it's exactly this syntax for, this is the syntax if you're non-reentrant, and there's another syntax that is not just a pointer to a variable, but a qualified pointer to a variable if the code is reentrant. And I don't see an example of that. There are a limited number of commands you can use to find out what's going on with the sequencer program that is running in an IOC already. You can show all the programs, and you can show the details of a particular, you can show the connected channels or disconnected channels of a program, and you can stop a sequence program.
And those are executed in the IOC shell.
Exactly right. Those are, yes, thank you. Those are executed in the IOC shell. Oh, that's right. You can also do a get callback and a put callback from SNL code, which is great because SNL code is a channel access client, and you really have to be able to do that. The syntax is quite different from the syntax in channel access or from anything else. It's basically sync or async attached to a CA put. And it's also, it's a little bit awkward to find out when that thing is done because it can be confused with other changes that also happen to to that variable.
Why
So-
would you do a get callback and put callback? Under which circumstances you would?
You would do a put callback if you want to know when that operation that you started, presuming that you're going to start some kind of an operation like move a motor, you would do a put callback if you don't want to continue until that thing has finished.
Okay.
But
That
if you
is-
don't-
okay.
And you can assign PV names to code at runtime also if you want. So that means programmatically assign them with information that you might not have at boot time. And some of Mark Rivers' databases use this a lot because he doesn't know how many channels there are at the time he wrote the program. So he programmatically assigns PVs when he finds out at runtime what the number of channels is. So it's very useful, and you really do have to read the manual because this is a complicated. It's a complicated beast. It's like C code. You can get into a lot of complicated situations with C code and also with SNL.
Could you point us to an example of such a program?
I have an example. I could show you an example in the optics module of a. So this is the program behind that high heat load monochromator that I showed you in the optics table, in the optics talk. And this was originally written in 1995 by Ned, and then we stopped making comments on it quite a long time ago. It still has been modified, but we just sort of abandoned the practice of including comments. So you're going to see a lot of assigned statements, right? Codes of CTL debug so that the user can say, I want you to tell me what's going on, because I have to figure out how this program works, or I have to figure out why this program is crashing. And so I always have debug statements in there. Then there are a bunch of PVs that are basically constructing a user interface. So we're going to be looking at the PVs that an Epix user is going to write on that MBDM display that I showed you, where you can type in the Miller indices and the crystal species and the wavelength you want. That database is basically the user interface, and this code is executing according to what it's watching that database and learning what to do by watching that. So there are the Miller indices, and so when the user writes into that, we're monitoring those things, and we have an event flag associated with those guys, so that whenever L is written to, we're going to get an event. And that's going to start our execution. So there's a whole bunch of those things, because there's a lot of variables associated with the monochromator. And they all look the same. So we're going to want to know when the theta motor is done moving and when the Y motor is done moving, so we're going to have to attach to all of that stuff. We need to see the limit switches for all those guys to make sure that the user isn't accidentally trying to tell us to know that the motors haven't actually hit limit switches. We need to know the limits of all those motors, so that if a user types in an energy that would violate that, we can make sure that doesn't happen. Actually, I think what happens is we translate all those motor limits into energy, wavelength, and theta limits. Well, I guess energy and wavelength limits. So we're not even in the code yet, right? We're still assigning variables, and there's just going to be a whole bunch of variables because it's a complicated user interface. Even though it's not that complicated of a screen, but you end up writing a fair amount of code just to implement the user interface. And then a whole bunch of tweaks, like wasn't bad enough as it was just to have those motors. You also want to be able to tweak them forward and back. There is an offset, a beam offset, which tells you what equations to use in order to move those crystals as the monochromator energy changes. And then here are some variables that we don't want the state notation language program to look at, or some statements we don't want the compiler to look at, because it's not going to understand string.h and math.h. It doesn't want to see that. And it also doesn't want to know about this, which is going to be our internal function that figures out what the 2D spacing is from the Miller indices. That's not an SNL program. That's going to be an escaped C code, which we'll see later at the very end. So finally, the first state set is, so there's an initialization, and this guy's going to go through and check that all of the motors are in some reasonable range that makes sense. He's going to go through them one by one. So you can get the macros that the user specified on the command line. I don't remember why that's happening here. Oh, because the user interface wants to be able to tell the user which motors are associated with theta and y. And the SNL program doesn't by default know that. So it has to get that information from the macros that the user supplied. So I'm not really sure, I mean, I don't think we want to go through the details of it, but just the structure, right? There's going to be a lot of states. Wait for command to enter. Did somebody change energy? Did somebody change wavelength? Did somebody change theta? Did somebody hit one of the tweak buttons? And then I think there's another state set down here. Good ways that, yeah, there's a separate state set that just keeps the motor independent fields updated, it says. And then the motor, the monochromator as a whole has a set use field similar to what we saw with the motor, so that the user can say, adjust everything. Now I want to call this energy 7.3 kilovolts instead of I want that to pass through to the motors to change the motor calibrations. And then here are the C routines that the state notation language compiler is not going to pay any attention to. We get to call this code and completely define it. So that's it for the...
In order to compile this file, just put it into the source directly.
Yes, if it has the right prefix .st, and you have to include that file in the sources, but the make knows what to do with an ST or STT program. I don't remember what the difference is between those two prefixes. I think one of them runs it through the C preprocessor first and the other one doesn't. So in the Synapse XXX module, there's an example of SNL programs, or no, in the optics module in the source, there's an example of SNL programs being So now we're just building a library here, but you can see optic sources is cosine CTL.st, all the other, so that's all you have to do.
The code is run through CPP for STT.
I'm sorry?
The inner lines. For suffix.
Oh, yes, thank you. For,
ST code is run through CPP.
for STT, it's not.
It's not-
Wow, that was a long time ago. I
yeah.
forgot all about that. So, are there any other comments or questions about state notation language? You guys gotta be beat, man. This is a long day.
So I have other questions.
I'm sorry?
I have other questions.
About other things?
Yeah.
Right? Okay, cool. Questions that we should include in the record or just, no? So then that means we're basically done?
Yeah.
Okay, we're done.
Thanks, Alex.